Welcome to Algeomelis Prep Academy. The lesson for today is sequences or series using limits and the n-term test. The n-term test for divergence states, if limit as n approaches infinity for a sub n is not equal to 0, then the sum from n equals 1 to infinity of a sub n diverges. However, if limit as n approaches infinity for a sub n is equal to 0, then there's no conclusion about the series for convergence or divergence. It works because if an infinite series converges, its terms must get infinitely smaller. But if the terms don't approach 0, you're adding forever, forcing the sum to grow infinitely, which also means it's diverging. Example number 1. We are asked to determine whether the series diverges or state that the n-term test is inconclusive for the sum n equals 1 to infinity of 2n plus 1 over n. So we begin with taking the limit of n equals infinity of 2n plus 1 over n, and to simplify, we get that the limit to infinity approaches 2, which is not equal to 0. Looking at the individual terms of the sequence, this makes sense. As n gets greater and greater, we approach the value 2. We now know that the sequence a sub n converges to 2, which means as n gets larger, the terms of the sequence get closer and closer to 2. Using the n-term test, since limit as n approaches infinity for a sub n is not equal to 0, then the series, the sum from n equals 1 to infinity of 2n plus 1 over n diverges. This makes sense as the series adds up all the terms of a sub n, and if each term of a sub n approaches 2, we are repeatedly adding numbers near 2 an infinite amount of times. Therefore, the sum grows without bound, and therefore the series diverges. Example number 2. For this example, we are asked to determine whether the series diverges or state that the n-term test is inconclusive for the sum from n equals 1 to infinity of square root of n plus 1 minus square root of n. Once again, we must begin by finding the limit to infinity for the sequence, square root of n plus 1 minus square root of n. In this case, we can use conjugates, which simplifies to limit as n approaches infinity of 1 over square root of n plus 1 plus square root of n. We then can plug in infinity, getting us 1 over square root of infinity plus 1 plus square root of infinity, simplifying to 1 over infinity, which approaches 0. We now know that the sequence a sub n converges to 0, which means as n gets larger, the terms of the sequence get closer and closer to 0. Since limit as n approaches infinity of a sub n is equal to 0, we have no conclusion about whether the series converges or diverges. Another test is necessary to make a conclusion.
Moving on to example number 3. So we're going to determine whether the series 2n to the fourth over 4n cubed plus 3n minus 7 diverges or is inconclusive via the n-term test. So by taking the limit to infinity, we plug in infinity, we'll eventually realize that we end up with indeterminate form in the form of infinity over infinity. So now we can use L'Hopital's rule, which involves taking the derivative of the top and bottom of the expression. So if we do so a few times, we get the expression to simplify down to just n. And what this means is that the limit as n approaches infinity of 2n to the 4 over 4n cubed plus 3n minus 7, same thing as the limit as n approaches infinity of n, which just equals infinity. Now what this means is, since the sequence diverges, we'll essentially be adding larger and larger numbers in the series, meaning therefore the series also must diverge.